Welcome to Understand the Math. In this Calculus 1 video, we're learning how to use implicit differentiation to find derivatives of functions that define y in terms of x implicitly instead of explicitly. We'll start by reviewing the difference between explicit and implicit functions, then outline a step-by-step method for finding the derivative of an implicit function. We'll then work through multiple examples, including finding the equation of a tangent line and even a second derivative using implicit differentiation. Be sure to download the free guided notes to follow along and work through the examples with me. Let's start by looking at the difference between explicit and implicit functions. An explicit function is a function of the form y is equal to f of x, where y is defined explicitly as a function of x. This just means that y is related to x by a formula. Here's two examples. In our first example, we have the function y is equal to the square root of 25 minus x squared. This is just the upper half of a circle, which I have graphed here. Our second example is a sine wave function y is equal to sine of x. And I've placed the graph of this one down here as well. Both of these examples that I've listed are examples of functions. And the reason for that is that at any point along the x-axis, if we take a vertical line and have it pass through our function, it's going to intersect our function at only one point. The same thing happens over here with our sine graph. When we have explicit functions just like this, we already know techniques for calculating the derivative dy dx. Let's now talk about implicit functions. An implicit function is a function defined by a relation capital F of x comma y is equal to 0, where y is implicitly defined as a function of x. This just means that y is related to x by an equation. Let's look at two examples. The first example is a circle centered at the origin that has a radius of 5, and I've graphed it right below here. And then the second equation is really long. I don't think I'm going to read this off, but I'll go ahead and I'll highlight it. It is called a cardioid, which is why the graph looks like a heart. Let's now see what happens if we do what's called the vertical line test and pass a vertical line through our graph. There's one, and here's the other. These graphs are different than the ones we looked at right above because here our vertical line intersects our graph at more than one point. That means that these graphs don't represent a function and instead represent two or more functions. Whenever this happens, we can't find the derivative using one of the rules that we've learned before. Instead, we need to learn how to use implicit differentiation for calculating the derivative dy dx. And that's what we're going to do next. We are now going to learn a method for finding derivatives of implicit functions. Implicit differentiation is the technique that we're going to use to find the derivative of an implicit function that is defined by the relation capital F of x comma y is equal to 0. When we use implicit differentiation, we are going to be given the function capital F of x comma y is equal to 0, or this function may look like capital F of xy is equal to a constant, or capital F1 of xy is equal to capital F2 of x comma y. No matter what format we're given, our job is going to be to find the derivative dy dx. I have written down 3 steps that we can follow whenever you have to use implicit differentiation. The first step is just to differentiate both sides of the equation. Let's highlight both sides of the equation with respect to x. And then the second step is you're going to group terms with dy dx on one side, and then put everything else on the other side. And then the third step is that you just have to solve for dy dx. In this green box, I have listed what I think is one of the biggest stumbling blocks for students when you do implicit differentiation. One of the key things to remember is that if you have a function y of x and you take the derivative, it is dy dx. That part seems pretty straightforward. Let's now look at the function y squared of x. When you take the derivative, you are going to get 2y, and then you're going to have to multiply that by dy dx because y is a function of x. And then the same thing happens for any power of y. Your derivative is going to be n times y to the n minus 1 times that dy dx. So just remember to multiply by dy dx whenever you differentiate a power of y. Let's now walk through an example so that you can see how the three steps that I've outlined above actually work in practice. We are given the equation x squared plus y squared is equal to 25. That's just a circle centered at the origin with radius 5. And we want to find dy dx. The first step is to take the derivative with respect to x of both sides of our equation. So we're going to take d dx of x squared plus y squared, that's the left side, is equal to the derivative with respect to x of the right side, which is 25. Now we go ahead and take the derivative. The derivative of x squared is just 2x, and then the derivative of y squared is 2y, and then here comes that dy dx that we have to multiply by. And then on the right side, we have the derivative of a constant, which is 0. Our second step is we are going to put dy dx on one side and everything else on the other side. So we have 2y dy dx here on the left, and we're going to move the 2x to the right, and that is a minus 2x. Now our third step is to just isolate dy dx on our left-hand side. We have dy dx, and we're going to divide both sides by 2y, so this is minus 2x divided by 2y, and then the 2's cancel, and we're left with an answer of minus x divided by y. And that's our derivative. We are now going to walk through 5 examples where we need to use implicit differentiation to find the derivative. In examples 1, 2, and 3, we are going to find dy dx by implicit differentiation. I have written down the 3 steps that we can follow just to make it easier, and we will go through these steps as we walk through our examples. Let's look at our first example. We are given the equation 1 plus x is equal to sine of xy squared. We're going to start by differentiating both sides of the equation with respect to x. So this is d dx of 1 plus x is equal to d dx of sine of xy squared. The derivative of 1 is 0, and then the derivative of x with respect to x is 1. And then on our right-hand side, the derivative of sine is cosine. So we have cosine xy squared times the derivative of what's inside. On our left, we have 1, and then on our right-hand side, we have cosine xy squared. And now we're going to use the product rule. Here's our first function, and here is our second function. The product rule tells us that the derivative is going to be the first, which is x, times the derivative of the second, which is 2y times dy dx. Remember, whenever you differentiate a y, you have to multiply by dy dx, plus our second function, y squared, times the derivative of our first, which is just 1. Since we eventually have to solve for dy dx, Let's go ahead and let's multiply everything through on the right-hand side. This gives us 1 is equal to 2xy cosine xy squared. Notice I just rearranged the terms. And then we have a dy dx plus y squared cosine xy squared. It is standard to put a variable before a trig function. Now for our second step, we are going to get everything with dy dx on one side and everything else on the other side. So I am going to take our y squared cosine xy squared and I'm going to bring it to the left. So this gives us 1 minus y squared cosine xy squared is equal to 2xy cosine xy squared dy dx. Now we're going to solve for dy dx, and that is our third step. So let's divide everything by our 2xy cosine xy squared. I am going to go ahead and flip both sides just so our dy dx is on the left. So we have dy dx is equal to 1 minus y squared cosine xy squared, all divided by 2xy cosine xy squared. And that is our answer. Let's now look at our second example. We are given the equation the square root of x plus y is equal to 1 plus x squared y squared. Just like we did for the first example, we are going to start by taking the derivative with respect to x of both sides. I am going to rewrite our square root as x plus y to the 1/2. And then on our right-hand side, we have d dx of 1 plus x squared y squared. Let's go ahead and now take our derivative. The derivative on our left is 1/2 x plus y to the minus 1/2 times the derivative of what is inside. That's the derivative of x plus y. So this is 1 plus dy dx. And then on the right-hand side, the derivative of 1 is 0. And then we have to use the product rule. We have a first function and a second function. So our derivative is going to be the first function x squared times the derivative of y squared, which is 2y dy dx, plus our y squared times the derivative of x squared, which is just 2x. Now we have to do some algebra simplification. The first thing I'm going to do is I'm going to take our x plus y to the minus 1/2, and I'm going to bring it to the denominator and make it a square root. So on our left-hand side, we have 1 plus dy dx in the numerator, and in our denominator, we have 2 times the square root x plus y. And then on our right-hand side, we have 2x squared y dy dx plus 2xy squared. We are working towards solving for dy dx, and I think the easiest way to do that is to go ahead and get rid of our denominator on the left-hand side. So I am going to multiply both sides by 2 times the square root of x plus y. This gives us 1 plus dy dx on the left. And then on the right, we have for our first term 4x squared y square root x plus y times dy dx. And then for our second term, we have 4xy squared times the square root of x plus y. Now we get to go on to our second step. We are going to put everything with dy dx on one side and everything else on the other side. Let's put this term and this term on the left-hand side. So we have dy dx minus 4x squared y square root of x plus y times dy dx. And then we're going to take our 1 to the right-hand side. So our right-hand side is 4xy², square root of x plus y minus 1. Now let's go ahead and factor out a dy dx. So we have dy dx times 1 minus 4x²y, square root x plus y, is equal to 4xy², square root of x plus y minus 1. Now for our third step, we can go ahead and solve for dy dx. So we're going to divide both sides by this expression. This gives us dy dx on the left is equal to 4xy², square root x plus y minus 1, all divided by 1 minus 4x²y, square root x plus y. When I was working through this problem, I looked at this when I got to this point and I thought, oh, maybe those terms cancel. But then I realized that in the top term, we have an xy², and then in the bottom term, we have an x²y, so they are not the same. So this is our final answer. Let's now look at our third example. This one has a trig function in it. In this example, we're going to be finding dy dx for the equation tangent of x minus y is equal to y divided by 1 plus x². Let's start by taking the derivative with respect to x of both sides. D dx of tangent x minus y is equal to d dx of y divided by 1 plus x². Now we can go ahead and take the derivative. The derivative of tangent is secant squared of x minus y times the derivative of what's inside, and that derivative is 1 minus dy dx. And then on our right-hand side, we have a quotient. We have a term in the numerator and a term in the denominator, so we are going to use the quotient rule. The quotient rule tells us that the derivative is the bottom term, 1 plus x², times the derivative of the top, which is dy dx, minus the top term, which is y, times the derivative of the bottom term, which is 2x. And then we could divide all of that by the bottom term squared. Now we need to simplify this. I think it's easiest if we don't have denominators, so let's multiply both sides of our equation by 1 plus x² quantity squared. This gives us 1 plus x² squared, secant squared, x minus y, times 1 minus dy dx. And then on the right-hand side, we have a 1 plus x² dy dx minus 2xy. Since we want to find dy dx, I think the best thing that we should do is multiply everything out so we can separate the terms out. On the left-hand side, we have 1 plus x² squared, secant squared, x minus y, minus 1 plus x² squared, trying to write small here, secant squared, x minus y, dy dx. And on the right-hand side, we don't have to do anything, and we just write this as 1 plus x² dy dx minus 2xy. Now what we're going to do is we are going to pull everything with a dy dx onto one side and everything else on the other side. I'm thinking because we have a negative right here, it's probably going to be best to pull the dy dx terms to the right and everything else to the left. So let's write this as 1 plus x² squared, secant squared x minus y. And we're going to pull the 2xy from the right to the left. So we add 2xy. And then on the right, we have a 1 plus x squared dy dx. And then we're going to add 1 plus x squared squared secant squared x minus y dy dx. I think the hardest thing of implicit differentiation is solving for dy dx. And I just realized that this was our second step, so I'm going to put a 2 there. Now we need to solve for dy dx. So let's clean up this right-hand side. I am going to pull out a dy dx from both terms, and then notice that each term also has a 1 plus x squared. So let's go ahead and let's pull that out too. 1 plus x squared, and then we're left with a 1 plus a 1 plus x squared secant squared x minus y. Now for our third step, we are going to solve for dy dx. And let's switch sides just so that the dy dx is on our left. So on our left, we have dy dx. And on our right, we have the term that was on the left, 1 plus x squared squared, secant squared, x minus y, plus 2xy. Now we're going to divide by all of this. And that is 1 plus x squared times 1 plus x squared secant squared x minus y. And there is our final answer. Notice that we could not cancel out a 1 plus x squared because this term didn't have the 1 plus x squared with it. We're now going to look at a different type of problem. For this problem, we are going to find the equation of the tangent line to this curve at the point 2, 1. This curve is called a cardioid because it's shaped like a heart. And what we're doing, if you look down here at our graph, is we are finding the equation to the tangent line of this curve at this point right there. Let's start by writing down what the equation of our tangent line is. It is y minus y1 is equal to our slope times x minus x1. Our slope, m, is the derivative of y with respect to x at the point x is equal to x1, which in our problem is equal to 2, and then y is equal to y1, which is 1. Let's now find our dy dx. Looking back up at the equation in the upper right that's highlighted in yellow, we are going to take the derivative with respect to x of both sides of that equation. So we have the derivative with respect to x of x squared plus y squared minus 1 quantity squared is equal to the derivative with respect to x of 4 times x squared plus the quantity y minus 1 squared. Looking at our left-hand side, we are going to use the power rule to find the derivative. So that is 2 times x squared plus y squared minus 1 times the derivative of what's inside, which is 2x plus 2y times dy dx. And then on our right-hand side, our first derivative is 4 times the derivative of x squared, which is 2x. So we have a 4 times 2x. And then don't forget that that 4 multiplies through both terms. And I just realized that I need an extra parenthesis there. So we have a 4 times the derivative of this term, which is 2 times y minus 1 times dy dx. Now, I'm going to show you something here that makes things a lot easier. We could go through all the algebra and solve for dy dx, but we don't need to because we are going to be plugging in that x is equal to 2 and y is equal to 1. So let's go ahead and let's do that now. We are going to plug in x is 2 and y is 1, and that is just going to make things so much easier. So we have 2 times 2 squared, which is 4, plus 1 squared, which is 1, and then minus 1. And then we have 2 times x, so that's 4, plus 2 times y, which is 2 times dy dx. That's what we're solving for. And then on the right, we have 4 times 2, which is 8, times x, which is 8 times 2, so we have a 16. And then we have an 8, and y minus 1 is actually 1 minus 1, so that's going to be 0 times dy dx. Let's see what we have on our left-hand side. We have an 8 times 4 plus 2 dy dx, and then on our right, we only have 16. Let's divide both sides by 8, so we have 4 plus 2 dy dx is equal to 2. And this gives us 2 dy dx is equal to 2 minus 4, which is minus 2. And if we divide by 2, we can see that dy dx then is equal to minus 1. We are going to take this answer then and go ahead and plug it in for our slope. Let's go ahead and let's write down our equation again. We have y minus y1 is our slope, x minus x1. y1 is equal to 1, so we have y minus 1. Our slope we found to be negative 1, and then we have an x minus x1, which is x minus 2. Let's go ahead and let's multiply things through. This is y minus 1 is equal to minus x plus 2, which gives us that y is equal to minus x plus 3. And that is the equation of our tangent line to our curve. Let's go back up to the top here because I want you to notice that our answer, y is equal to minus x plus 3, matches with that pink line. It has a slope of negative 1 and it has a y-intercept of 3. Let's now do one more example. We are going to use implicit differentiation to find a second derivative, d squared y dx squared, for the curve x cubed plus y cubed is equal to 1. We are going to start by first finding dy dx. So we're going to take the derivative with respect to x of both sides of our equation, x cubed plus y cubed on the left, and then the derivative with respect to x of 1 on the right. On the left, we get 3x squared plus 3y squared. Don't forget to multiply by dy dx. And then the derivative of 1 on the right is 0. Now, we could go ahead at this point and solve for dy dx, but I actually think that's harder because dy dx then is going to have a numerator and a denominator and be a quotient, and we would have to use the quotient rule to find the second derivative. So what we're going to do now is go ahead and find d squared y dx squared by taking the derivative with respect to x of both sides of this equation. Let's go ahead and let's do that. That's d dx of 3x squared plus 3y squared dy dx. That's on the left. And we have the derivative with respect to x of 0 on the right, which is, of course, going to be 0. Let's look at our left-hand side. Our derivative is going to be 6x. And then we have two functions, 3y squared and dy dx. So we are going to have to use the product rule. So this is the first function, 3y² times the derivative of our second, so that's d²y dx², plus our second function, dy dx, times the derivative of our first, which is 6y, times dy dx. And on the right-hand side, we have 0. Now let's go ahead and let's highlight that we want to find d²y dx². So let's keep that term on the left and let's pull everything else to the right. This gives us a 3y² d²y dx². And on the right, we have a minus 6x minus 6y, and then we can combine the dy dx's and make that squared. Now let's get d²y dx² all by itself. So this is a minus 6x minus 6y times dy dx quantity squared. And we're going to divide all of this by 3y². Now what we have to do is go back up to this line right here, and we need to find dy dx. So dy dx is going to be minus 3x², all divided by 3y², which gives us minus x² over y². Now we're going to take this and plug it back in for this. This gives us a minus 6x minus 6y times minus x² over y², and then that is squared, all divided by 3y². Now we just have to simplify this. Notice that we can divide the 3 into the minus 6's, and we're just going to get minus 2's. So we have a minus 2x minus 2y, and then in our parentheses, we're going to square everything. So that's going to become x to the 4th over y to the 4th, and we're dividing all of this by y². Let's now separate this out. Our first term is minus 2x over y², and then our second term is minus 2. Notice that this y cancels with one of these y's, so we're going to have a y³ there. So we have a minus 2x to the 4th, and then we're going to have a y³ times a y², which means we have to add the exponents. So 2 plus 3 is 5, so we have a y to the 5th. I think this is going to be nicer if we get a common denominator of y to the 5th, and this leaves us with minus 2x y³ minus 2x to the 4th. And then for our very last step, let's pull out a minus 2x. So we have minus 2x, and we have then y³ plus x³, all divided by y to the 5th. And then if we want to be really fancy, we can go back up to the very top and notice right here that x³ plus y³ is equal to 1. So we can plug that in, and we get an answer of minus 2x all divided by y to the 5th, because this term was equal to 1. And then that is our final answer. And that's it. You've learned how to apply implicit differentiation to equations that define y in terms of x implicitly. You've practiced solving for dy dx, finding equations of tangent lines, and even working with second derivatives. To really master these types of derivatives, make sure you work through plenty of practice problems on your own. If this video has been helpful to you, please consider subscribing to my channel. Keep believing in yourself and have a great rest of your day.